So day 2 now in this section. Now we're going to be looking at some tests to find zeros by hand. Just want to say up front, I'm not doing this to torture you. This is so you have to take a really hard look at what pieces of polynomials lead to the different zeros you see and some of the behaviors you see. Every zero you have turns into a factor which impacts every piece of the polynomial, the shape, the end behavior, all those things. And that's what I'm really trying to force you to look at. So these are rules. You'll have to do all this stuff by hand. Make sure you check out all the stuff that's posted. I've got all these rules listed out. If I go too fast, you can pause it, but you can also pull them up later and look at them. So I'm going to try to really explain why these rules work like they do and the way these tests work. First one is called the rational zero test. And what we're going to do, I'm going to kind of lead you through it piece by piece. This might not seem like something you would ever do, but I think you're going to see where it's going pretty quick. So I'm taking a binomial, I'm going to distribute or FOIL it out, and I've asked you to leave it in an unfinished multiplication. So instead of saying 2 times 3 is 6, I'm writing that as 2 times 3 and I'm leaving it. So let's do the outside. That would be 2 times -1, and then that's going to have an x with it. This is going to be 3 times 3, so let's say plus 3 times 3 with an x. And then last times last is going to be plus 3 times -1. All right, I know that's probably not super clear why I would ask you to do something so silly, but now watch what's going to happen. So what would the first and last terms be as factors? Well, the first term was 2 and 3 as far as the factors go. The last term was 3 and -1 in terms of factors again, because those are the numbers that multiply to make what this would end up being 6. So 2 and 3 are the factors that make that. Okay. So what are the zeros? All right, we'll flash over to Desmos real quick. I have no doubt that you could find these zeros if you had to. That's not what I'm trying to question right now. So -1.5 would be -3/2. 0.3 repeated would be 1/3. So let's jot those down. So -3/2 and positive 1/3. Now, ignore the signs for right now. We'll get into that. But pause for a second and see if you can tell where I'm going with this. Look at your zeros. Look at the factors that you had in this step. Now, hopefully you kind of noticed that the numbers on the top here, the last term, those numbers showed up in these top numbers, the numerators, and these bottom numbers, the first term, the factors showed up in the denominators. And that's what I'm trying to point out. Now that's not good enough for a proof, and I picked something that's got 3 in both places. The signs are kind of probably not super clear right now, but hopefully you kind of see how that's starting to play out. And it's not coincidence. That was supposed to happen. And we can prove that it's always going to happen. So let's try to do a little mini proof here. And let's point out the zeros come from the first and last terms, or at least they're factors. So let's expand something that's all variables. So ax plus m times bx plus n. So first times first would be abx squared. Outside 2 would be plus anx. Inside would be mbx. And then last plus n times n. So that's the expanded form of that. So what are the zeros? Well, if we're going to find zeros, we set this equal to 0. So ax plus m would equal 0. And also bx plus n would equal 0. So ax would equal -m. X would equal -m over a. That's 1 0. Bx would equal -n. X would equal -n over b. That would be your other 0. So to try to make sense of this, why this is going to happen, sometimes in class I might get you to expand something that had 3 terms to it. And you know what, let's kind of take a look at that real quick. And I'm not going to do the whole thing, but just see how this would play out. So let's say there's another term, cx plus p. Well, your first term would be a times b times cx squared. You end up multiplying all those together. And your last term would be m times n times p. And if you think about what this extra solution might be, well, it would be cx would equal negative p when you set that factor equal to 0, and x would be negative p over c. So we see that thing playing out. The point is, the way you get your first term is by purely multiplying all your first terms together. The way you get your last term is by purely multiplying your last terms together with nothing else mixed into it. So the way you create a solution is to set that factor equal to 0. The solution only has the last term and the first term in it. So we can take factors of we multiply the polynomial out, take factors of the final term divided by factors of the initial term, and those will always produce our zeros. So that's kind of why the rule's working. So let me show you what the rule is. And we're kind of ignoring the signs right now. So here's the test, rational zero test. So you have a polynomial in this form. Let me kind of talk you through it. Some of y'all like this kind of stuff. I always have to sit back and think about it for a second. But f of x, a function. All right, this is what this is saying is a polynomial with powers that are counting down until you don't have a power on this last term. All right, you have x to a power, x to less than that, like x to the fifth, x to the fourth, and so on to your constant. And then some coefficient out front, in front of the x. So like 2x to the fifth plus 7x to the fourth. And then the powers will count down until you get to your constant, whatever that is on the end. Okay, so when your polynomials are in that form, this last term was a multiplication of all the last terms for the factors. This first term, this first coefficient, it was a multiplication of all the factors of your leading coefficients for each individual factor. So the way the rule works, if you break down this final term in your polynomial into all its factors, not just prime factors, but all of its factors, then any positive or negative version of those factors could be the numerator of your solution. And same thing with this leading coefficient right here. If you break down all the factors, we're going to do an example in just a second. If you break down all the factors, all the positive and negative versions of those factors could be a part of your denominator for your solution. Now this is going to make a pretty long list, but at least it narrows it down, and we do have a list. It's not an infinite number of possibilities anymore like it was when we started. When we started, this could have been any solution, maybe. So now we've got a definite list of possibilities. Assuming they're rational. If they're irrational, they're not going to show up on this list anyway. And if they're complex, they're not going to show up on this list. So if they are rational, though, this will show it up. So let's do an example just so we can see how it plays out. So find all the possible rational zeros of this polynomial. All right, well, what really matters is the final term and the first term. So I need all the ways I can make 14. And don't forget the most obvious, which is 1 times 14. So 1 could do it, 2 times 7. And I like to keep them in order like that. You can organize that differently if it helps, but I think in the end, it's really good to keep them in order. 10, well, you can do 2 and 5, you can do 1 and 10. Just don't forget the 1 times the final number. That's always one of your possibilities. It's easy to overlook. So those are all the ways that you could make 10. Those are all the possible factors of 10. And we need all the plus and minus versions of both of these. So to wrap it up, our list, all our possible zeros, and there's going to be quite a few here. Well, we could have 1 over top of any of these numbers. I just like to put a plus or minus out front. I don't think there's any need to do all the positive numbers and then write them again with a negative in front of them. I think it's fine if you just do something like this. Just put positive and negative in parentheses and then just list them out. So we could have 1 over 1, which is 1. We could have 1 over 2, which is a half. We could have 1 over 5. We could have 1 over 10. All right, and then we could have 2 over 1. And you're going to start to see some repeats too. You could have 2 over 2, which is 1. We've already got that. You could have 2 over 5, so 2/5 is a possibility. 2 over 10, which is 1/5. We've already got that one. All right. You could have 7 over 1. We could have 7 over 2, 7 halves. We could have 7 over 5. We could have 7 over 10. And then on to 14. We could have 14. We could have 14 over 2, which is 7. We could have 14/5. We could have 14/10, which would be 7/5, which we've already got. And that will do it. That's all the possibilities. So Still a fairly long list, but now you've narrowed it down. And if we're going to find all these zeros by hand, then you've narrowed the list down, so you've got to start. And that's where we'll pick it up from there a little bit later on in this lesson. But that's it. That's how you generate your list of all your possible rational zeros. All right, so this part's going to tie back into the factor remainder theorem. It's pretty much the exact same thing we've already done. I'm just clarifying something to really drive a point home. So the polynomial comes from the product of all its factors. How can one factor be used to find the rest? Okay, well, if you know any of the factors, you can always divide the whole polynomial by that. So divide the polynomial by one of the factors, and then it'll divide out, go away on that other side, and you'll be left with the remaining factors. That's what the whole factor remainder theorem is about. If you divide a factor out, the quotient part you're left with is the remaining factors. So you kind of whittle it down so that it gets easier and easier to find the zeros. And that's the process you did in Algebra 2, where you're given one zero, or maybe you had to find a zero, and you divide it out, and then you try to factor from there, or maybe you just have to keep dividing stuff out. So that's where that process, that's why it's valid, because if you have a zero, you can divide it out, and then you can continue to divide more of those out. I said zero factors. If you have a factor, you can divide it out. All right, so we'll try to make this one make sense to you. Descartes' rule of signs. I'll let you, if you want to pause, you can pause it here and read through this. It's also posted on Classroom, so that's fine as well. So what's going to happen when we get a polynomial? And I'm going to read through it. I know it probably won't sink in at first till you see it a few times, and that's okay. But I'm just going to read through it anyway. Number of positive zeros of a function is equal to the number of sign changes. So this is the thing. If you want to know about how many zeros you're going to have that are positive, we're going to be looking at sign changes as we go through the polynomial. Or a multiple of 2 less than that. That part probably makes no sense right now, and I don't blame you. So I'm going to draw it out with graphs. I think graphs are the easiest way to see this. You're going to get a problem of the week where you actually go through and prove this, so that's going to really help deepen your understanding of why it's working. But that's the main thing. Look for the number of sign changes as you go through your polynomial, just whatever the terms are. And that's going to tell you how many positive zeros you could have, or maybe a multiple of 2 less than that. And when you do when you find f of negative x, then the number of negative zeros, so zeros that are less than 0, the function has, or number of x-intercepts that are less than 0, let's put it that way. That's going to be equal to the number of sign changes of f of negative x. So you do f of negative x like you were finding if a function was even or odd, same process. And then you count the sign changes, and that tells you how many negative zeros you're going to have. Or some multiple of 2 less than that, which I'm going to explain that again. Okay. So let's just dive in here. Sketch all possible graphs of negative 3x cubed plus 2x squared plus x minus 5. I'm not looking for anything too exact. Just want you to pay attention to 3 main things. In behavior, y-intercept, number of zeros. So first up, we've got x cubed. So the ends are going to point opposites with disco function. And you got negative 3 out front. So let's see, a line that's negative goes down, left to right. So left side's going to point up, right side's going to point down. That's the way this is going to look. So left side pointing up, right side pointing down. That's what we're going to expect to see. So let's think about what could happen. All right. Well, y-intercept is always this constant at the end. So it's at negative 5. And the number of zeros, we should have 3 zeros. They may not all be real, but we should have 3 zeros. So at least 1 should be real. And hopefully that's kind of familiar from Algebra 2, but trust me on that. If not, I can maybe find something to help you review that idea. So here's what the end behaviors are going to do. This side's going to point up, this side's going to point down. Let's kind of run through what could happen. Let me slide those out of the way. Whoops, that didn't help at all. So let's see, if this end's pointing up, maybe it gets all 3 zeros out of the way before it ever crosses the x-axis or y-axis. Okay. Maybe it comes down and crosses one time, So similar shape to that, but scoot it down a little bit so it's only got one real solution. Now, in either case, it's got 3 negatives or 1 negative. Okay. I'm going to give it to you. There's 2 more possibilities. So, all right, maybe it comes down and crosses the x-axis, the y-axis, and then does something like that. Or maybe it comes down and crosses and then never quite makes it back up. So it looks like we could have, as far as negative negative solutions, we could have 1 or 3. This is where that multiple of 2 less comes in. It's just the way it works out. For positive solutions, we could have 2 or none. So again, negative solutions, you could have 3 or 1. For positive solutions, you could have 2 or none. So it's always, there's a definite possibility or any 2 less than that. These are all the possible arrangements of the functions. So those have to be the possible number of solutions we'll have. Now let's run through this part. Let's do f of negative x. We'll keep that visible so I can see it. All right. If I do f of negative x, the main thing is take, say, negative x and cube. All right, well, let's go make that term negative. So negative x cubed times negative 3 is positive. Again, I can explain it more if you need me to. Basically, all that's going to happen is all of your odd powers are going to change signs. Even powers are going to stay the same because negative x squared is positive x squared. So positive 2 times positive x squared stays the same. So this will become negative x. This will be minus 5. Okay. So let's kind of apply the rule now that we've done these 2 parts. Because what you're supposed to be able to do is not have to draw all these graphs, just count the sign changes and know what those graphs are going to have to look like. So for positive, this is the positive version, so this is about the positive zeros right here. All right, we went from negative to positive, that's a sign change. Stayed positive, went back to negative, that's 2 sign changes right there. So we could have 2 or maybe no positive zeros. And that's what we saw, 2 or maybe none. All right, let's run through the number of sign changes on this negative case. So start off negative, stayed negative, went positive, and then stayed positive. So that's 1 sign change, that's it. So there's 1 possible negative 0. And since you have just 1 negative 0, and you know that's it, just the 1, we can come back up here and kind of rule some things out. So this arrangement that fit all the descriptions, I mean, we didn't get all the zeros and see where they were, but this seemed like a possibility, but now we know there's only 1 negative 0, so this case can't happen. It's got to be one of these 3. So this kind of helps you narrow down your possibilities and start ruling things out as you're working toward finding the number of zeros. On their own, none of these tests really do a whole lot. When you combine them, we're going to put them all together to find all the zeros without a calculator. That's where this goes. So that's really all there is to that rule. Let's try that one more time just to see if you've got a feel for how it works. I'm not going to draw all the graphs out, but you could do that if you kind of want to just see if you got the idea. You could draw out every possibility. I mean, this is x to the 4th, so both ends point up or down. You got a negative leading coefficient, so both ends point down. Your y-intercept is going to be at 3. And then you could just draw out every possible, so look kind of like a letter M. You're going to draw all the ways that could happen. And think about where the possible positive and negative zeros could be. I'm just going to run through the test here. So for f of negative x, this is the positive version, so this is the number of positive zeros. So positive zeros. Possibilities, it's not definite. But all right, so we got, it's negative, then it goes positive. There's 1 sign change. Goes back to negative, there's 2 sign changes. So it's negative, goes to positive. That's 3 sign changes. So we could have 3 or 2 less than that. So we could have 1 positive 0. We can't have negative 1 zeros, so it's only positive numbers of possibilities here. All right, now f of negative x. So I put in negative x here, raised to the 4th. Sign stays the same. So negative 3x to the 4th. And again, what's really going to happen is all your odd powers change signs. So you really, once you get that idea, you don't have to do a whole lot of work here. Probably be able to do this in your head. So Let's count them. It's negative, it's negative, it's negative, went positive, stay positive. One sign change. So your negative zeros, you have 1. And then what you're going to start doing is combining this with all the possible rational zeros. And this would be a good place to start because there's a few possibilities for positive zeros, but there's definitely one negative. So I can start looking at my negative possibilities, start dividing the polynomial by those and seeing if something divides out evenly, making it a factor.